be on the edge.
Well, thank you for the invitation. So this talk, I think, is going to be a little different than some of the other ones, which different can be good or bad. So we'll see how it lands. But I'm going to be talking about some of the work that we do in my group, and we kind of focus on a bunch of different areas. So I'm going to just kind of start with like what our research philosophy is and the things that we do. So I come from a background of doing epitaxial synthesis of complex oxides, designing ferroelectric domain structures. We're not really going to talk about that much, so if you don't like ferroelectrics, it's fine. I do a lot of multidimensional spectroscopy of all different sorts, and I primarily work on the scanning probe microscopy, so we'll talk a little bit about that, but I also have kind of ventured into other sort of areas of advanced spectroscopy. And to deal with kind of the data and the size of the data that we have, I really need machine learning because we have a lot of valuable data and it's much harder to extract information from that data. So I figure out ways to kind of extract information from that data. And to do that practically, we really need to think about our computing infrastructure. So a lot of what my group has been focusing on is how do we actually make these machine learning models and machine learning tools usable and practical for the applications that we have. So I kind of wanted to go and start off with like, what are the practical requirements that we need for machine learning? So things like, how do we go about simply saving, searching, preserving, and sharing data? This kind of gets into that concept of the data deluge, where you have so much data and the data analysis, I think everyone can say, takes infinitely longer than the acquisition time. So you could think analysis kind of takes from weeks to months. So another problem is science is distributed all over the world. Everyone has their instruments and things, and data that is collected is rarely collated so that anyone else in the world can use it. This is a major problem. So you think about where you save your data, it's in folders and file systems. That's not good long-term. Another key problem is universities and even national labs don't really have the infrastructure that's required to manage data. There's no good networking that's around for actually moving large volumes of data. PIs are responsible for managing data, and most of them do not have experience in designing parallel file systems and systems that have reliability, availability, and resiliency for managing data systems. And the universities don't provide it, and if they do, it's at a really high cost, and usually it's not backed up. You'll find out that later. The other problem is doing the computation is slow. And I think one of the main reasons why doing the computation is slow is not actually the computational speed, but it's moving the data. So if you think about, if you're going to have a data set that's 1 terabyte, with standard internet speeds at universities, about a gigabit per second, it's 2.5 hours. And you can't even really write on most disk systems at a gigabit a second. So it's actually slower than that. And then you also have a problem of if you're doing scientific instruments and or experiments and you want to actually collect your data and analyze it in real time, the computation needs to be highly available. And most computing systems run on Slurm with schedulers, and that just doesn't work for experimental workflows. So another kind of problem that I think is really important is like machine learning is great, but how do we ensure that it's parsimonious? How do we ensure that it reflects the physics? I like this simple example. It's a little bit of an over-exaggeration, but if you start with a concept of a circle and you want to learn the concept of a circle, machine learning might say, okay, I have this concept of a triangle. And then if I take a bunch of triangles and put it around the circle, eventually I learn a circle. That's what machine learning does in a very kind of abstract level. That's not really useful because if we get a smaller circle, it has no idea what that is. There's no idea how to deal with that. So it's going to fail. So the question is, can we kind of impose more physics constraints and underlying governing equations or learn governing equations to enable us to actually learn models that respect the physics? So this is kind of a really important concept. And then the final area I think I'm going to cover is how do we conduct analysis in real time? And what is real time? Because real time can mean a lot of different things. It can be fast enough to guide experiments, it's kind of on the order of seconds. Be fast enough for closed loop control, that's seconds to milliseconds. And we're fast enough for on-the-fly data compression, which I think is probably one of the most important things, the most underlooked, where you're talking about milliseconds to nanoseconds that you need to do the actual data analysis. This imposes a lot of different challenges. You need to actually think about your hardware that you're using. So you need to think about every single operation, every single data transfer, where your memory is stored, and what is your hardware design. Because a lot of times the general computing tools like CPUs and GPUs are not useful for these applications. So kind of wanted to give a highlight to this talk, or say the secret of creativity is knowing how to hide your sources. So I'm going to hide the source of who did that, maybe because it wasn't actually listed. But a student once told me that my work was somewhat creative, and I'm going to prove that student wrong. So we're going to start. Can you play the video? So this was an example that I saw online. So this is something called platform.ai. And this is a tool that helps users go and they take images and they can create projections of those images and do really rapid labeling. So they sell it for some fraction of a penny per image. You can go in and you can create these different projections and explore similarity. So I thought, could I do the same thing for materials? So what do you need for this? So we need, okay, so you have a user, they collect some data. You need that data to be input into some platform. We need some sort of system that can deal with the data transfer, preservation system, backup to make sure that it's reliable and preserved. And then once you have all the image data, you need to be able to search and explore both the metadata and the data itself. So we work with with people at Oak Ridge, and they use this tool called DataFed. It's a scientific database. I don't have a lot of time to go into detail with it, but essentially what you can do is you can upload your data, uses Globus to do secure file transfer, and it also has a full metadata search tool so you can do logical queries on your data. So this is a really useful first component. Then the question is, how do we understand image similarity? So if we have our classical convolutional neural network, this is just a VGG19, so this is really old and outdated, but essentially what's important to know is it takes an image, and at the end you get a vector that's 5, 12, and 1. Okay, so that's your vector. That vector contains the similarity of all the images, or a vector that defines what the images are. Then you can go and you can do things like create projections using things like UMAP or TSNE. These are just different tools that kind of work that latent space, that 5, 12 dimensional vector, create things that are similar. If you look at images like classical image, oh, yeah, this thing is not good. You can see like people are grouped here. Up here, they're all the animals, which is really interesting because it was trained on cats, dogs, roosters, but it groups them all together up there because they're semantically similar. So the question is that says, okay, that learns a lot of high level information about the system, but can we do this on materials? And the answer is no. So if you go and you put in this sort of model trained on cats and dogs for materials, it doesn't work. You just get a big mess. And the reason is because materials don't care about things the features that cats and dogs care about. So we said, what do materials care about? And at a very high level, they care about order, symmetry, periodicity. So we said, okay, can we make a model that at least knows something about order, periodicity, and symmetry? So we took the wallpaper group symmetries, took random swatches of images from ImageNet, and recreated over 10 million examples of images. This data set's online, open, and available, that has the wallpaper group symmetries, the classes, has the unit cells, a bunch of other metadata. We trained a model. This model works surprisingly well. That's a misnomer. It's not actually learning symmetry. It learns symmetry when the data set is created from this set or this distribution, but it doesn't actually learn symmetry. So we tried to validate this by creating a different data set that has the same symmetry operators, and it doesn't learn symmetry. So if I can figure out that problem, I'd be very, very happy. But nevertheless, it does learn some semblance of symmetry. So if we start to create projections like they did in that platform.ai example, you can see that a lot of things are kind of grouped together. So this is a data set of 25,000 random piezo response force microscopy images taken just from a file system that's like an AFM that someone had sitting there. And we can go and we can see, okay, this is an area, these all look similar. This is all CA domain structures grouped really well together. This is some stripe phase BFO, and this is some mixed phase PZT. So it groups the things that have the same microstructures together, which is really useful if you want to discover data in just a collection of raw data sets. You could play this and maybe skip to the middle. So then we kind of wanted to say, okay, could you do something more like make recursive searching? So if you can go in and you can go explore around this latent space, select regions of interest, and then once you select regions of interest, you can create new projections in that region of interest, and then you get refined results. So I mean, I'm not going to be able to show because it takes a little while, but you can look at this reference, and this tool is all online, and we're refining it and making it even better. So can you play this video as well? So this is like really useful because we want to try to augment how we do experiments. So this is an example from Lehigh at the Nano-Human Interface Initiative. So being able to have, so this is a data collection, but also have a interactive module, and this is done with HoloLens, where you can go and you can see the crystal structures and make comparisons and similarities is a really powerful tool. So this is a little 3D crystal structure explorer that you can use while you're on the microscope. So we're kind of building this infrastructure to do this image similarity search and have more tools that help augment users while they're on the instrument. So automating this pipeline, which is very time consuming and is difficult. If you make someone do even one extra step as an experimentalist, they probably won't do it. They probably won't save their data. So automating and making it as part of the standard workflow is really important. Getting the data into a database, special tools for doing searching when you don't have a metadata schema that's as well defined, because we can fight about schemas forever. It's just better to try one and have it adapt over time. And then these interactive tools for image similarity searching. And this is just really to help people explore and discover their data a little better. The next kind of topic I'm going to talk about, changing gears a little bit, is parsimony. So I was just browsing YouTube, and I think one person I really like is Nathan Cutts at University of Washington. And he does a lot of work on trying to learn underlying governing equations. So this is an example where you have a Lorentz function, and it's actually a neural network that uses sparse identification of parameters, so from selected parameters, to learn the underlying governing expressions. And so I said, okay, could we use this same concept in material science to accelerate different workflows? So we do this experiment that's very common called band excitation piezo response force microscopy. It's developed out of Oak Ridge National Lab. The key point is that we're going at every single pixel position, we apply a bipolar triangular waveform that switches the material, and then you're measuring the dynamic response of that material, the cantilever, by measuring the cantilever resonance at a band of frequencies. So this is a multi-frequency measurement, and what you want to do in this data set is you want to fit these individual cantilever resonances to a simple harmonic oscillator model. And those are coming out at about 4 milliseconds per individual resonance response. And if you wanted to do this in real time, could we do this? So here's like kind of what the raw data stream is. If you have the magnitude and phase spectra, you can fit this to this as a just classical simple harmonic oscillator model. Nothing too complicated. And the question is, could we use a neural network to do this fit, but do it under the guise of having to follow the physics? So what we did is not that complicated in terms of we take the raw data, use conventional 1D convolutional neural networks. We do some little tweaks with message passing that kind of help. There's a lot of little tricks and things that make it perform better, but the general concept works pretty easily. But what we do is at the end, we have a dense layer, end layer that predicts the 4 parameters needed for the empirical function. And because this is still differentiable, we can use auto differentiation, train this end to end, and we can train this completely unsupervised, but still obeying the physics. So if we look at the results, they look essentially the same as the least squared fitting. That's kind of good. That's what we would expect. But things get a little more interesting when you look at the distribution. So with least squared fitting, you're really reliant on the initial guess and where that initial guess is. And if your initial guess is wrong, you get trapped in a local minimum, and then you get responses that look like this that are not physical. So these are actually bad fits, these tails of the distribution. The neural network on real data always tends to be much more uniform in distribution. So that's a little hint that it's maybe doing a little better in some ways. If we look at the raw data that a person would extract, it looks essentially the same. There's no difference. So that's a good sign. But things start to get kind of more interesting when you start to add noise. So if you add noise based on the standard deviation of the raw data, you start to see that as you start to add more noise, this least squared fit tends to not fit the data at all. It gets trapped in a local minimum, and then you end up not fitting your result well. And you'd have to build in a lot more robustness to the model. This is a fairly robust, commercialized process. And like you can see here, the phase is like just completely irrelevant to the actual phase of the raw data, which is shown over here. So what this is showing is that the neural network's able to be much more resilient to the noise in the data. And we'll show kind of more examples of that. So you can see kind of down here, like this is the least squared fit of the noisy data. It doesn't show anything, but you still see the domain structure. This means you can deal with much lower signal to noise ratios by using neural networks in creative ways. So now I'm going to give another example of this, and I think this is kind of relevant to what Maria talked about. This is kind of learning from 4D STEM. So this is kind of work done with David Muller, Colin Ofis, Yimo Han. And in this problem, we have a diffraction pattern from scanning an electron beam. So you get this diffraction pattern. What we're interested in determining is the strain and the rotation. So that's like how much the diffraction pattern strains and what its orientation is. So we said, okay, could we make a toy data set? So Colin Ofis did a multi-slice simulation where he made random grains with very sharp or perfect strain profile, so -2 to 2%. For both the strain and the shear at random rotation angles. We said, could we learn this? First, we wanted to see like what would the current models do. So this is Colin Ofis's Pi 4D STEM with all the like manual tweaking and tuning to get it to work exactly as right as we could. And we can see that it does pretty good, but there's still some areas that it's not recreating the peaks that we would really like. We know what the ground truth is in this case. So we thought, could we make a machine learning model that could do this? So we start with our input data, and then we think about how we can do this. So we can say, okay, we can try to have some sort of encoder that learns some statistical representation. And we have two kind of blocks of this model. The first block is like a classification layer. So this K-top just classifies it, says choose one of many. So this is identifying what types of crystal structures we have, what the primitive representation of the crystal structures are. Then we have something called this is called a spatial transforming layer. So what this does is it takes this encoded information and tries to learn the theta matrix of an affine transformation. So that's just doing things like translation, rotation, shear, and strain. And then we can take that learned affine transformation, apply it to the initial input. And if we're learning the strain, we have a reference point here, which is our learned representation. We can compare that, and if we get a good result, that means we learn the strain. To help the training, we do something known as training it cycle consistently. So we take the inverse transform of the theta matrix, so the inverse of the theta matrix, apply the inverse affine transformation, go back and also compare it to the original. That just solves some problems. With the right tweaks in terms of regularization strategies added to the model, we can get really good reconstruction. So that, let's say the dots all line up, which is good. That's a good sanity check. But then we should really compare it to the ground truth. So if we look at the left, we show kind of the best from Pi 4D STEM. We look at our neural network, we're getting the much sharper peaks, much sharper distributions. That's saying that we're doing actually a much better job than the conventional algorithms at actually learning the strain. And the cool thing is that our neural network is giving us the real strain value. It's trained unsupervised. We don't give it any labels, but it's learning the number for the strain because we included the physics in it, which is physics of an affine transformation. So then the question, does this work on real data? So this is a data set from David Muller, Tungsten selenide. And here's the Pi 4D STEM result. This is our result. It looks a little sharper, a little better resolution, but a little more contrast in the images. But where things get really cool is we can go in and we can reduce the electron count. So we can say, okay, here's the number because it's a direct electron detector. We can say randomly have a random probability of that electron existing, and we can get down to 2% and still be able to resolve some of the key features. So this is way lower dosage for some of the sensitive materials. So this is a really kind of interesting result and a nice way of using machine learning. So this really matters if we want to kind of go and this is some of the work from Oak Ridge, trying to use this for doing deep kernel learning and automating experiments. If you want to have intelligent systems in the pipeline, you should use as much of the physics at intermediate steps as possible. So these are just kind of two examples where in this case, they're doing learning how to switch a material. But as you include more and more physics in the model, you're going to get much better results. So now I want to talk about kind of the last topic. So I was at a random conference, and I think it's always good to go to different conferences, and I was hearing a talk about how they deal with the data at the Large Hadron Collider. So this is the LHC, and the problem that they have here is they're at 40 megahertz. They are collecting data on the order of petabytes per second. So that is physically impossible to save to disk using any strategy. So the key problem is that they need to do data reduction. They need to, most of the events that they're observing are useless. They're not anything interesting. So they need machine learning models that perform at the speed that's required, so for about 40 megahertz in the kind of 100 nanosecond range, that is able to do data compression on the fly. Choose which data is important, and then kind of going to the pipeline of doing subsequent data reduction at lower and lower or longer latencies. So the question is, how do you do this, and can we translate this to material science? Just to kind of quick fact is that this is 10 times the average internet traffic in North America, just to kind of give a kind of sense of the scale. But we're not that far off in terms of material science. So like this is electron microscopy, and now we're up to like 200 terabytes per hour. That's a large amount of data. These sort of strategies need to be deployed. So we're kind of in the tabletop version of the Hadron Collider. So the thought is, how can we go about doing data reduction? And if you're going to do data reduction, we can't move the data because the network infrastructure isn't there. So the only way to do it is to do real-time reduction. That means deploying models on ultra-efficient hardware. So using field programmable gate arrays on the edge so that you don't have to worry about the network infrastructure. You can just use local high-speed networking and do the data reduction on the fly. Now that creates different problems for training your machine learning models because you have less resources. You can't rely on like the large-scale parallelism and leadership class computing. But from a practical standpoint, it's much easier and it's much faster. So we work on this toolkit, and one of the challenges is like, I'm a material scientist. None of my students know anything about hardware. They don't know what HLS is. They don't know what Verilog is. These are the ways that you write code or write like you're physically writing the electronic circuits in the chip to make them run this fast. So what we worked on, and we worked on this toolkit called HLS for ML. And essentially what it does is it takes models trained in Keras and TensorFlow and does with some compression and conversion and a bunch of other little bells and whistles that I don't have time to talk about today. We'll do conversion to this, what's known as HLS, which is high-level synthesis. And then that can be compiled into IP blocks for FPGAs. So what this does is it takes the design cycle that maybe would be months to a week in terms of doing these sort of deployments. So this is just one example of kind of one deployment of that fitting function for the simple harmonic oscillator model. So we're able to do streaming inference. So this is just the forward pass on the order of 12 microseconds per fit, which is incredibly fast compared to about the 1 CPU second that it would take on like if you're doing a least squared fitting. So that's in that case, it's way faster than we actually need. It's just the hardware is so beefy. But in some of the like electron microscopy applications, we need to put some fairly large models in at like 50 microseconds. So the question is, on what does this enable? So it really enables us to do more complex experiments. It opens new windows into how you can conduct new experiments. So like in my lab, we do something called reflection high energy electron diffraction to look at surface crystallography while we're doing pulse laser deposition. And because of the cameras and the data management, most people use cameras that are 60 hertz, 120 hertz. But there's a lot more information if you start increasing that and you know how to deal with that data. So this is an example where we're doing read at 500 hertz, and then we're doing the fit of the diffraction spots in real time on FPGAs. And that allows us to see things like watching the diffusion coefficient or measuring the diffusion on the surface because we're able to see it in real time. We have enough temporal resolution. So it's just, but each one of these experiments is about 4 to 8 terabytes of data. So managing that is challenging. But then you can start to see like, okay, there's effects of surface treatment, there's effects of step width that you don't see when you normally do these sort of measurements and these sort of experiments. Another kind of example that we're doing in my lab is, and I don't know why that's so small, usually it's not that small, but in my lab, we have a camera that images at 10 million frames per second that we're able to measure the plume dynamics during pulse laser deposition. So that's real, that is actually hundreds of nanoseconds time resolution that you're seeing. And what we're trying to do is we're actually working with Nathan and trying to understand the plume dynamics and learn the underlying governing equations, because we want to do things like, instead of just setting and forgetting our synthesis, like the old rotisserie chickens. We want to actually go and we want to control and stabilize it. So we know that during our growth properties change. We see our plume changing, all these things change. Because we have no control over anything because we don't know how to adjust it. We don't have any eyes on the actual plume dynamics. So what we're doing is we're building closed loop control systems just even to stabilize our growth dynamics during the process. So that's the first step before then we can start to automate and do more complex things. But if we want to actually program a synthesis process where you need to change parameters during the synthesis itself, you need these sort of control systems and you need to be able to visualize the dynamics of the system. So that, I think it's I'd like to conclude. So I talked a little bit about some of the work we're doing on image similarity, and we have a database that we just recently got an NSF award for that has over a petabyte of data storage, and we're going to make 250 terabytes available to the community. So if you're interested, please email me, let me know. Talked about how you can include physics constraints in neural networks to accelerate fitting and to do things like strain mapping, automatic strain mapping. And then talked a little bit about kind of how we can where we can take some inspiration from the world of particle physics for real-time machine learning on FPGAs. So that I have to acknowledge some of the students that helped do this work. A really nice, diverse group. And I'd say a lot of what I've been able to benefit from is really pulling out some students, especially undergrads who know all this hardware engineering that are able to kind of implement and tinker with these systems. They're really, really great when you get them. And they're very excited to work on some of these fun problems. So that I'd be happy to take any questions. And thanks again for the invitation.
Thank you, Josh, for a very fascinating talk. We have some questions.
Hi, it's a really nice talk, and hopefully I can catch you before you leave for the day. I had a question about the real-time analysis that you showed with the FPGAs and just before. So 320 gigabits per second, is that correct?
Yeah.
How high a frame rate is that? I think it's 4 million.
That's like at 5,000 frames per second. I think it's 4K.
Okay.
And then full bit depth, yeah.
Got it. And why FPGAs? Why not a GPU?
Okay, so the reason why, so a GPU and CPU, they're useful if you want throughput, or at least the GPU is, because they're all single instruction, multiple process components. So that means that your CPU needs to send a message, a command, then it does the computation. With an FPGA, we build the computation into the hardware, so you skip that latency-ridden step. So if you're going to do anything on a GPU, your latency is going to be at least 2 milliseconds for a single example. That's why, like, if you're going to do like streaming inference, it's sometimes better to do it on a CPU. It really depends on it depends on the workflow, but the FPGAs are just way faster for streaming inference because you don't have that latency.
And is that important, like 2 milliseconds? Because it's like you said, the throughput is very high. So just like a constant latency difference.
It depends on the application. So I mean, if you can get away with a GPU, that's fine. But if you want to do controls and compressed sensing and more intelligent things, we need to have that. We need to have that latency. Also, getting the data to the GPU tends to be a little bit more tricky than getting it to an FPGA because FPGAs have better built-in protocols for streaming data directly. So this is kind of the challenge. The FPGAs you just have a lot more control than you do with the GPU, I think, if you're going for latency constraints. If you're just doing throughput, GPUs will beat it because you can always parallel. I mean, most of these processes are embarrassingly parallel, so you can just parallelize it more and add more GPUs. It's easy. It's only when you care about latency.
Awesome. Thank you.
More questions from the audience? Can I ask you a question? I'm completely naive when you go. Oh.
Yeah, go ahead.
So I'm very naive. I don't know anything about hardware, but so what you're doing, so how easy is to integrate your instruments and the signal that is coming out of the instrument to the FPGA to do inference in real time?
So I wish it was easier. That's probably the biggest pain point is figuring out how to get the data streams in, because a lot of our instruments have proprietary data acquisition systems. So it depends on how they allow us to hack into the data stream. And then if you're trying to really hit these latency requirements, like, is there other latencies that they have in terms of doing it? So like the cameras have been really easy because like we have a phantom vision camera that goes right into an FPGA IP block, and we can just run the data right off of it. That's why it's because that's a little more of a standard protocol. The electron microscopy stuff is a little harder because the vendors need to open it up, but we need to push on the vendors to open up the raw data streams.
Thank you. Yes.
Is it on? Thank you so much. Very nice talk. I really like the image similarity comparison. Is your model available publicly?
Yeah, I mean that model for the symmetry aware model is
Right.
posted online. It's an NVIDIA
Okay.
computational materials. We have all the code. It's all reproducible.
Great, because we would love to run it
Yeah.
on a whole bunch of different
Yeah.
data sets. Yeah, thanks.
We have a couple of questions, in Slido. There's a question, did you do an area under the curve on fitness and accuracy of the model? I don't know for which model.
But I don't know which model, and usually we didn't in these cases because like most of the time we were going to a physics constraint, so we had a real validation that we didn't need to do something like a area under the curve sort of fit. It wasn't as relevant in these applications.
Okay, there's another comment there.
With a lot of numbers.
Yeah, I mean, GPU latency is around in the 10 microseconds, not nanoseconds. If it's 10 nanoseconds, I wouldn't care. Like the message passing the latency is somewhere in the order of like 500 microseconds just to send that message command from the CPU to the GPU to get it to start. And then you have to think about the IO rates as well, which are not as well optimized as FPGAs.
Yes.
When you're doing real-time control, pulse laser deposition, what do you detect and what do you control?
Yeah, so we're working on doing the real-time control. We haven't done that full. What we're really working on is building a model to control the plume dynamics. So we have our camera and we can watch the plume dynamics, and we want to stabilize those plume dynamics because we see a large variation in the plume dynamics.
What knobs do you turn to minimize it?
What knobs do we turn? So we have what we can control. So we can control our optics or focus, so that affects our fluence. We can control our laser energy. We can control our gas flow rates. All these.
As your substrate starts getting consumed,
As you're depositing from a target onto a substrate, your plume changes its shape pretty significantly because the laser absorption changes as you start to ablate the surface. And we adjust generally. You need to increase your energy through the deposition process, and you need to increase your fluence. But right now we don't have any controls, and you don't have a way to look at it. So what do? We set it once, and we forget about it. And when you look at it, it starts out, the plume looks this big, and then it goes to that big at the end of the growth. And that can't be good. That creates a gradient. So we're trying to solve simple problems before we address the bigger ones. Who said we need to talk?
I don't know, like an enormous person, but can I ask you a question? So for the physics constraints, like when you're trying to fit a model, like the one-dimensional model or the 4-parameter model that you had, I don't remember what physics was there. So the only thing, I don't want to say the only thing because it's pretty sophisticated, but to do the constraint, you just added a dense layer at the end of your network that predicted the parameters that went into the physics of the equation that you were trying to fit, right?
Yes, and as long as it's differentiable, you can train it end to end as an autoencoder. It's just the decoder is the physics. So after you train the model, it does a really, really good job at guessing the parameters. And you can validate it after because you can look at the response and you can do kind of all those validations that you do. But the decoder is just the physics. So I don't know how it learns the details of how to do the fit. It's really overfit, but it doesn't really matter because all that matters is that at the end it's constrained to be just the physics, and it's feed forward once it's trained.
So you could have a bunch of networks with different dense layers representing different models, and then you can do.
Yeah, so that's what I was showing with Nathan Cutts. So actually, what he does is he'll have a bunch of different candidate parts of expressions, and you can add regularization constraints to learn sparse mappings of those. So you can say, I'm going to slowly tweak my model using regularization, so like a damaging mechanism, to limit it to just a few of those, and then it learns the underlying governing equations. And that's something we're working on. That's a much harder optimization problem. And in this case, like a simple harmonic oscillator, we know the physics, so we're going to just use it.
But I can imagine there are a bunch of models that we material scientists know that we use, like constitutive laws, right? For the behavior of materials. They represent different underlying physics and theories on what is going on, but you could imagine having competing last layer where you have these different constitutive models, right?
Yeah, so you can have it so that it selects which model it thinks is best and then gives you the parameters.
Yeah.
Which is really powerful. It just makes the optimization harder.
I say we have like maybe one last question over there.
Yeah, thanks for the nice talk. Regarding the strain map, to quantify the elastic strain of current state. You know, in the mechanical deformation, and people also care about the plastic strain. You take an initial like a configuration, you load the structure evolve, which is the plastic strain, the strain accumulated from like an initial state. Can you comment like with the technique you have for this stem? Can you measure like the strain like from the beginning? Maybe you can take the real image and consider their part and input to the like diffraction.
Yeah, so I don't want to embarrass myself because I am not an advanced electron microscopist. I work with electron microscopists who provide me the data. So I might refer you to someone like Andy, who's a better expert and going to give a better answer than I will. But I think that's the best answer I could have. I worked more on the analysis side of this in this problem. So.
Let's thank our speaker again. And now we're going to have our panel and the last